Hi guys, welcome to Unit 5 Notes B2. Today we're going to learn about ozone bond enthalpies. So you may have heard that the ozone layer is there to protect us, and maybe even heard about some of the things that are eating it away and how dangerous that can be. So today we're going to look at why the ozone layer is so useful. And you can see here that the main purpose really for us, or the main benefit that we get from it, is that it is going to block some of the dangerous radiation that comes from the sun. And we're going to look specifically at the bond enthalpies of the ozone so we can see why it is so effective at this protection. Let's start with the problem that asks us to connect energy to wavelength. Now, what formula do we know that combines those two things? Well, we had energy is equal to Planck's constant times the frequency, but then again the frequency is equal to the speed of light over wavelength. So this is one of our formulas that we used the first time we were talking about light in Unit 1B. So here's this formula that's going to help us attach energy to wavelength. Keep in mind that Planck's constant is 6.63 times 10 to the negative 34th joules times seconds, and the speed of light is 3 times 10 to the 8th meters per second. So if we can find the energy, we can plug this in to get our wavelength. Here's the catch. This bond energy is not the same exact units of that energy in this light formula. This energy is the energy of a single photon. This is how much energy that photon would carry from a single electron transition. But bond energy is not the same. So let's take our bond energy, 363 kilojoules per mole, and see if we can't convert it into kind of the same units as the energy in our light formula. The first thing is, the formula on the right, the light stuff, deals with joules, but the bond energy is given in kilojoules. So let's fix that real quick. We're going to put kilojoules on the bottom and joules on top with 1000 joules per kilojoule, and so we have very easily converted kilojoules to joules. Now here's the hard part. This is energy of a photon that we need on the right, and on the left right now we have energy per mole. So how do I get rid of units that I don't want? I make them cancel. So if I have mole on the bottom, I'm going to put mole on the top. And now the question is, what would I convert moles to? Well, remember Avogadro's number explains how many particles of anything is equal to 1 mole. So I can have Avogadro's number of photons just the same as I could any other particle. So we have moles now canceling, so my units here would be joules per photon, which now does match my energy that I can plug in to the light formula. So when you do 363 times 1000 divided by Avogadro's number, you're going to get 6.03 times 10 to the negative 19th joules per photon. There we go. So that is our answer so far as converting, but we still need to go up and plug that into the energy along with these constants in order to solve for our wavelength. Alright, so I had to make a little space here. I've got the energy that we just solved for, and then our two constants, and I want to plug all of this into our energy formula. So on the left hand side we've got the 6.03 times 10 to the negative 19th. And then on the right hand side we have our two constants, which are going to be over the wavelength. So x in the denominator, as you're familiar with, we have to multiply both sides to get that out of there, and then to isolate our wavelength, we're going to now divide by our energy. And so when you crunch this all in the calculator, Planck's constant and the speed of light times the speed of light and then divided by the energy, you're going to get 3.30 times 10 to the negative 7th meters, and that's going to be per photon. So you'll see your seconds cancel, your joules cancel, and you have meters per photon. So that is our wavelength that each photon would have. And as you may remember from honors, with light, especially in the visible range of the spectrum, we don't leave it in meters, so we can convert this into nanometers, and that would be 330 nanometers, because 1 meter is equal to 10 to the 9th nanometers. So you can do your dimensional analysis there. There's our wavelength of light for something that has a bond energy, ozone, having a bond energy of 363 kilojoules per mole. So now we've connected that bond energy into the wavelength of light for that molecule. So this is the slide from the PowerPoint with it all worked out. I just wanted to show the two separate formulas here, which I combined and used all together. And then just to point out, you don't have to show your work of converting kilojoule to joule. If you're used to doing that on your own, that's fine to go ahead and pick it up there. And then here is our conversion factor from meter to nanometer. So a couple of pieces to fill in the blanks there if there was anything you missed. So before we start comparing oxygen and ozone, let me just point out where those numbers are that we just found. We used the bond enthalpy of 364 kilojoules per mole to determine that the wavelength would be 330 nanometers. So now I want to look at both ozone and oxygen, and we're not going to do the whole calculation on oxygen, but here are the results you would get using its bond enthalpy to find the wavelength that's optimal for it. And I want to compare these two and then talk about why they're a little bit useful. So let's start with the Lewis structures. For regular diatomic oxygen, we would have a double bond with two lone pairs. And I know they're drawn a little bit funny in IB. Sometimes each of these lines would represent our lone pairs. So that double bond is the only thing that exists for the oxygen, and so when we look at the bond enthalpy, we're looking at the breaking of that double bond. So a double bond here. Now with ozone, you get one double bond and one single bond, and that molecule would experience resonance. So the true structure of ozone would have two sigma bonds, with the pi bond being delocalized over all three oxygens. So we have kind of single and double bonding going on with the ozone. So now let's talk about something called bond order, which I think may be the first time we're really talking about bond order. IB doesn't have a whole lot to say about bond order. If you want to see a definition, they literally barely mention it in a text box on page 167. And all they really say is that a single bond has a bond order of 1, double bond has a bond order of 2, a triple would have a bond order of 3. And then the resonance is kind of a halfway because it's delocalized, and so if you're between 1 and 2, it's a 1.5 in terms of bond order. There is a whole lot more to bond order, but not that IB cares about. So that's all we need to know, is that the bond order for oxygen is greater than the bond order of ozone, and so then you're going to see a stronger bond, more energy required to break that bond, as opposed to something with a lower bond order. And the strength of the bonds we have talked about, where single bonds are the weakest and it takes the most energy to break up the triple bonds and so on. Now let's focus on the important part, this connection between bond enthalpy and the wavelength. You can see that the oxygen requires more energy, like we just talked about, because it has the higher bond order, less energy for the ozone. But it's an inverse relationship to the wavelength. Higher energy absorbs lower wavelengths. Lower energy absorbs higher wavelengths. So energy is inversely proportional to wavelength. I shouldn't use proportion, not equals. And that kind of can be seen from the formula over the wavelength. So if you're increasing the energy, I should probably do it the other way around. If I increase the wavelength, I'm getting a smaller energy, or if I decrease the wavelength, I get a larger energy. So you can kind of see how math-wise that would work out. So these are inversely proportional. As the energy increases, the wavelength decreases. Now these wavelength zones themselves are important. What this means is this is the amount of energy, this is the wavelength of light that would break the bond that required that exact amount of energy. So if I'm trying to break ozone's bond, I would need a wavelength of about 330 nanometers. So if this wavelength of light is being used to break the bonds, then it's not being transmitted down to Earth where it can hurt us. This range right here is right where your UVB and UVC light rays, the dangerous ones, kind of lie. So we want to try to block that from reaching the Earth, which is perfect job for the ozone layer, because the breaking of their bonds is going to require these dangerous wavelengths of light. So that's the big connection there. We are using up the wavelengths of light that are dangerous because there are reactions happening that break these bonds. So what we're going to look at next are the reactions in an equilibrium that exists that establishes this ozone layer where the bonds can be continually broken and reformed, always using up this light. The equations that we're about to look at are very particular, and it takes time to copy them exactly the way that they are, including all of the phases, all of the subscripts. We're going to look at something called free radicals, where you use a little dot to the side of the atom. It's all very particular. So my advice would be to copy these equations down. The pages of the book are right on the note takers. To go ahead and have them copied down, so that way when I'm discussing them, you're not worried about the particulars of copying the equations, that you have them already and can kind of follow along and annotate. So first let's look at just the pure dissociation of an oxygen molecule and an ozone molecule. So the oxygen molecule would start off as the O2 gas, our naturally diatomic molecule. And if it has this perfect wavelength here, about 242 nanometers, then it'll break the oxygen apart into two separate oxygen atoms. And we've learned that oxygen can't exist as a free radical here on Earth. But we are going to now start talking about intermediates and things that play a role in other reactions and multiple steps of reactions and things like that. So just because these things tend to be very unstable and get used up right away doesn't mean that they aren't steps in the process. So we are going to look at this equation here where the oxygen does break into the two separate atoms, but when the atom has an unpaired electron like this, we call it a free radical, and this is the notation we use. Now let's look at ozone's dissociation. So first our O3 will get rid of one oxygen and become O2. But now this free radical here is not going to stay out there forever. So one thing that could happen is that the free radical joins up with another ozone molecule, and so that would then kind of create these two stable oxygen molecules. So basically ozone dissociation takes ozone and kind of transmutes it into, or transmutates it into oxygen. So it's changing ozone into oxygen. This is a very exothermic process, particularly the last step, by the way, which is really important because there's a certain role heat plays in all of this as well. Notice how all of the phases are gas. So the fact that this is an exothermic process, a favorable reaction to change the ozone into oxygen here. The next thing we're going to talk about are things that can destroy the ozone layer. So as you can see, this is a busy slide, so make sure that you have these equations already copied down as we get into all of this. There's two main things that can destroy the ozone. One is a nitrogen oxide, whether it's a monoxide or a dioxide, works similarly. We're going to talk about the monoxide. And then also something called chlorofluorocarbons, or you may have heard them called CFCs, which have made kind of a big hot button issue in environmental studies. So now I want to look at the equations that cause so much problem with the ozone layer. So first let's focus on the nitrogen monoxide or dioxide. These are byproducts of combustion engines, which is exactly the kind of engine that your car would run on. So anything that's burning fuel is going to be a combustion engine, propane grills, things like that. So these combustion reactions are going to produce free radicals, which we talked about how those are so reactive, of either NO or NO2. So see with the dot there, we were talking about free radicals in the air. And these come out of the combustion engines in the gas form already. So when they make it up to the ozone layer, they're going to react with the ozone and produce a more oxygenated nitrogen compound. And so then my ozone becomes oxygen. So now you have NO2 in the ozone layer, but one other thing floating around in the ozone layer is these oxygen radicals. We talked about how that's produced from the decomposition of, or dissociation I should say, of the oxygen molecules. So if these two things meet up, then we get the NO free radicals and then oxygen. So what's happening overall, the net effect, is that the ozone is reacting with the free radical to form the oxygen molecules. The NO free radical cancels out, as well as the NO2 free radical. But because of their positions, we would call them different things. One is a catalyst and the other is an intermediate. Now, intermediate we've talked about recently. That's something that's produced in one step of the reaction and used up in another step of the reaction. Just like with energy cycles. If something goes through, I should call this B, goes through something else, A forms B, then B forms C, B would be our intermediate. So because we're forming NO2 and then using it up, that's our intermediate. There is a reaction that's the direct pathway from A to C. This reaction we looked at as part of ozone's dissociation on its own. The thing is, having this intermediate allows it to happen more quickly. But here's the catch. This intermediate wouldn't exist but for the original catalyst. So the catalyst is the thing that starts off the reaction, and you can see that it comes out of the end reaction unchanged. So the catalyst does not change during the course of the reaction. It instead provides an intermediate, which is produced and then used up, and then reforms as its old self again on the other side. So the catalyst would be what we start off with and end up with that ends up canceling out, whereas the intermediate is the thing that's produced in step 1 and used up in step 2. Neither the catalyst nor the intermediate are part of the net reaction. Now let's talk about our chlorofluorocarbons, or CFCs. As it turns out, what's so dangerous for the ozone is the Cl free radicals, but there is a preliminary reaction that's not really part of the whole main chain over here that needs to occur first in order to produce these chlorine free radicals. So chlorofluorocarbons have two chlorines and two fluorines. And the bond with the chlorine is going to break more easily since fluorine's more electronegative. And so the first atom that would be removed would be the chlorine. So the rest would stay together as a free radical, and then we get our chlorine. From there, this molecule may continue to decompose depending on how much energy is available, but it's this chlorine free radical that we now have in the ozone layer that creates such a problem. The chlorine free radical is going to react with the ozone to produce oxygen. So it's another way of ozone turning into oxygen. And then we get a different free radical this time, the ClO free radical. Then when that free radical connects with an oxygen free radical, which remember those are in the ozone layer also, then again you're getting oxygen, and now we're back to our original Cl free radical. So again, we need to be able to identify catalyst and intermediate. So the catalyst is what you start off with that gets changed around but then spit back out as exactly the same thing. So it's the thing that starts the whole process here. Our catalyst is the Cl free radical. The intermediate is the thing that is produced and then used up in the next step. So neither one of these things are in the final equation here. but we do have Cl radicals as a catalyst, and then that allows the reaction to happen faster using the intermediate of ClO radicals. So now we've looked at two ways that these pollutants can cause the ozone to turn into oxygen, which doesn't sound like a catastrophic problem, but the problem is that it's happening too quickly. There is a natural order of how this transaction and this interaction between ozone and oxygen is supposed to go, and that's called the Chapman cycle. So we're going to look at that next. So here's our Chapman cycle. Its goal is to keep the ozone at something called a steady state. And at the steady state, the amount of ozone is supposed to be approximately at 10 parts per million. So ppm is a unit we may not have seen before. It literally means like 10 ozone molecules per million of other molecules around in the ozone layer, so parts per million. So ideally we want the ozone itself to be at least 10 parts per million for us to be at the steady state. So we don't want the ozone turning into the oxygen too fast. We want to keep this equilibrium. Now let's look at the steps of the ozone depletion in the stratosphere. So first of all, this is going to be happening right around this 242 nanometers we discussed, where the oxygen would dissociate into those two oxygen free radicals. This is the same first step that we looked at back on oxygen dissociation. And then what's going to happen in step 2 is that our oxygen is going to run into a free radical and become O3. So in step 2, it's kind of the opposite of all the breakdown. This is the step that we may need to be happening faster if we keep breaking ozone down too quickly. We can form ozone by combining the free radical with oxygen. And there's an equilibrium that is naturally reached between the two. But ozone breaking down into oxygen is typically requiring a lower energy, and so that's going to be more slow. That's where you have the wavelength of about 330 nanometers. So that reverse reaction there is important for the equilibrium to be established. All right, then when we have, so say we're on this side of the equilibrium, when we have our ozone, if the ozone combines with a free radical, then that breaks down into the oxygens, which is supposed to happen very slowly given the absence of our chlorofluorocarbons or the NO free radicals. That's the way things are supposed to work according to our Chapman cycle. Alright guys, that's going to do it for the end of notes B2, kind of a little side quest into bond enthalpies and how they can affect the ozone layer. Our next set of notes on note C will kind of pick back up on Hess's law and get into energy cycles a bit more. So we'll see you there.